Welcome back, Focus Learners. Today's explainer is all about a literal structural game changer in software architecture. We're talking about the factory method pattern. Now, if you've ever felt completely overwhelmed by design patterns, or, you've opened a textbook only to be hit with confusing, totally unrelated examples, well, you're in the right place. We're bringing high energy today, and we're going to conquer this pattern using our own custom, dynamic examples. We're leaving that dry textbook theory in the dust and looking at exactly how and why this pattern actually works in the real world.
Okay, let's dive into this. Here's our roadmap for the explainer. First, the problem with new. Second, enter the factory method. Third, simulating animals with factories. Fourth, decoding the UML structure. And finally, scaling with asteroids.
Section 1. The problem with new.
Right, so before we can really appreciate this pattern, we have to understand the core friction that makes us actually need it in the first place. I love this quote. Dependency injection is programming by wishful thinking. Think about it. When we use dependency injection or apply something like the strategy pattern, we're beautifully abstracting our object usage, right? We're essentially pretending that we already have the exact object we need, just passed right into our method or constructor. We sit there in our code and say, let's just assume I already have this thing that does all this complex work. It's fantastic for abstraction, but it kind of ignores a harsh reality of programming.
And that harsh reality is this bottleneck right here. Someone, somewhere, absolutely must use the new keyword. I mean, unless you're building an application exclusively out of static methods, which, please, definitely do not do that, instantiation is just inevitable. At some point, you have to new up your classes. The real question is, where do we do that? Especially when the instantiation logic isn't just some simple one-liner, but actually requires complex business logic to figure out which parameters to pass, or even which specific class to construct. We need a uniform, nicely encapsulated place to handle all of that.
Section 2. Enter the factory method.
This is where we bring in our structural hero to encapsulate that complex instantiation. Let's look at the formal definition. This is popularized by the classic Head-First Design Patterns book. It states that the factory method pattern defines an interface for creating an object, but lets subclasses decide which class to instantiate, deferring instantiation to subclasses. Okay, if you're reading that and thinking, wow, that sounds incredibly abstract and a bit dry, do not worry. I promise you, we are going to break this abstract concept down into highly practical, super relatable pieces.
But first, we really need to talk about ditching the pizza. If you've read those classic textbooks, you know their main example revolves around a pizza store making New York versus LA style pizza. Honestly, if you aren't intimately familiar with the moisture content of regional American cheeses, it's just confusing. It completely distracts from the code. So, we are completely skipping the pizza today in favor of dynamic, interactive scenarios that actually make sense.
Section 3. Simulating animals with factories.
Let's set up our first concrete scenario. Imagine we're building a national park simulator where different animals spawn dynamically into a forest environment. First up, we need a shared animal type, like an interface or a superclass. Underneath that, we have our concrete classes: dog, cat, and duck. Now, our main simulation loop just wants an animal to jump around the forest. It shouldn't care which specific animal is spawned. So the crucial point is that our main code shouldn't care about the how. To solve this, we build an animal factory interface to handle all that underlying business logic. Our code just asks the factory for an animal, and the factory delivers.
And this brilliantly illustrates the sheer power of polymorphism. Let's compare two concrete subclasses of our animal factory. Over on the left, we've got a random animal factory. It's totally stateless. You call create animal, it rolls the dice, and boom, gives you a dog, cat, or duck by pure chance. On the right, we have a balanced animal factory. Now, this one is stateful. It actually remembers what it created in the past to make sure that over time, there's an equal number of dogs, cats, and ducks running around the park. Both factories implement the exact same method signature, returning an animal, but they use entirely different logic. Your main program just calls create animal and stays blissfully aware of the complex balancing or randomizing happening behind the scenes.
Section 4. Decoding the UML structure.
All right, now that we have a really tangible example, let's map it back to that formal UML jargon you're going to see out in the wild. Think of this mapping as your personal decoder ring. In standard architecture diagrams, you'll see the abstract term creator. In our world, that maps directly to our animal factory interface. The concrete creator represents the subclasses actually making the decisions. So that's our random animal factory and balanced animal factory. The product is the shared interface of what's being made, which is our generic animal. And finally, the concrete product represents the actual instantiated data, the dog, the cat,
and the duck. See? By tying those dry terms directly to our simulator, the jargon suddenly makes total sense.
Real quick before we move on, I want to clarify something you might encounter, the simple factory. The textbook actually calls this a non-pattern. And why is that? Well, if you just extract duplicate creation logic into a single method in one class, hey, that's a great refactoring step. It absolutely cleans up your code, but it's not the factory method pattern. A simple factory lacks the top half of our UML diagram. It lacks that abstract creator interface that allows you to swap out multiple interchangeable subclassed factories. You know, like smoothly switching from our random factory to our balanced factory dynamically at runtime.
Section 5. Scaling with asteroids.
Let's move to and see how this builds into a scalable game architecture. This is our most advanced application today. In any arcade space shooter, you have an iterative game loop that runs constantly, right? Step 1, the loop lap begins. Step 2, you call your obstacle factory. Step 3, you execute the create asteroid method. And step 4, a new asteroid spawns on the screen. Because you're using a factory, the game loop itself is incredibly clean. It literally just asks for an asteroid at every single tick over and over again.
But here is where developers hit a massive, massive pain point. As your game scales, you obviously want level 1 to be easy and level 10 to be absolute chaos. The initial instinct for a lot of us is to hardcode it. You make a level 1 factory for slow asteroids, a level 2 factory for slightly faster ones, and so on. Guys, this is a trap. Doing this will inevitably cause a massive class explosion. Your architecture will just bloat out of control with dozens of almost identical factory classes just to manage these slight variations in game states.
So what's the actual solution here? Parameterizing the asteroid factory. Instead of a brand new class for every single level, we pass computed parameters into one unified factory. We pass in properties like velocity x, velocity y, a speed multiplier, and size likelihood. Now, when the player hits level 4, our program simply passes a higher speed multiplier and a higher large size likelihood into our single factory. The factory takes those parameters and dynamically alters its creation logic, instantly spawning faster, bigger asteroids.
And this leads us to the ultimate aha moment of this entire pattern: composition over inheritance. By parameterizing a few key factories, you create literally infinite behavior variations. You completely remove the need to manually subclass every single new game state or level. You literally turn what used to be rigid, hard-coded types into flexible, dynamic properties. Your game loop stays perfectly clean, your factory logic is neatly encapsulated, and you have total control over the complexity of your objects without bloating your codebase. It is a real game changer.
So I want to end this explainer by leaving you with a bit of a provocative question. I want you to look at your current codebase right now. Where do you have a sprawling web of tightly coupled classes or just repetitive instantiation logic? Where could extracting all of that into a flexible, parameterized factory save you from an impending class explosion? Remember, the factory method isn't just some dry textbook theory about pizza. It's an incredibly powerful tool to clean up your architecture and scale your applications seamlessly. Thanks so much for joining me on this deep dive, focused learners. Now take this concept, go open up your IDE and refactor